Hello students, in the previous class we have learnt about the rate of reaction and the factors affecting the rate of reaction, and today we will learn about the rate law expressions, rate constant and order of reaction and molecularity of the reaction. So first we will learn about the expression for the rate law and order of reaction. In the chapter chemical equilibrium, you have learnt about the law of mass action, right? So according to the law of mass action, we know that the rate of a chemical reaction is proportional to the concentration of the reacting species. That means with respect to time, the concentration of the reactants, it gradually decreases, and with respect to time, the concentration of the products, it gradually increases, right? So let's take an example so that you will understand it properly. So for a general reaction of the type A plus B to products, here small a and small b represents the molar concentrations of the reacting species A and B. So according to the law of mass action, we can say that rate is directly proportional to the concentration of these reacting species. So it will be A and B. Now here the molar concentrations are raised to the power of each of the reacting species. Clear? So according to the law of mass action, we can say that rate is directly proportional to the concentrations of the reacting species. So if we remove this proportionality symbol, then it will turn to be rate is equal to one constant will be here, and the rest of the things will remain as it is. So here this shows the rate constant. This is called the rate constant. Rate constant of a reaction is given by small k in this way. Okay, so we can say that this is the theoretical value. Okay, here we have whatever theoretical way we apply to balance a chemical reaction, that is represented in this way. But what happens? Experimentally, the rate of reaction sometimes does not obey the theoretical values, and in that case, whatever quantity, whatever molar concentrations that take part in the chemical reactions, they are used to find out the rate of the reaction. So if we say that here in case of this type of reaction, suppose alpha amount of A and beta amount of B react to form the product. So in that way, we can say that experimentally, in that case, the rate will depend on the alpha and beta concentrations. So we can write it in this way, A and B. As this was a theoretical one, we will write alpha for A and beta for B. Now for the rate constant, it will turn like this. Okay, so here this is these A and B, they are the molar concentrations of A and B, and this K is the constant called the rate constant. So what is rate law now? Rate law is the expressions which express the rate of reaction in terms of molar concentrations of the reactants. Now here we can see that some amount are raised to the power. So these are the molar concentrations which are raised to the power. Okay, these values may or may not be the same as the stoichiometric coefficient of the reactant as it is expressed in the balanced chemical equation. Okay, so we can say that here these are the experimentally calculated values. Now what is rate constant? This rate constant, this K rate constant, this is called the rate constant. So it is the rate of the reaction when the concentration of each of the reactant is taken as unity. So we can say that the rate constant can also be called as the specific reaction rate. Okay, now we need to know that what are the characteristics of the rate constant. See, rate constant is a measure of the rate of reaction. That means greater is the value of rate constant faster is the reaction. So first we can say that the main characteristics of the rate constant is that it is the measure of the rate of reaction. Now see, this is the term rate constant. That means for each and every reaction, the value of the rate constant is fixed. So each reaction has a definite value for the rate constant at a particular temperature. If we change the temperature, the value of the rate constant of that reaction will also change, because we know that on increasing the temperature, the rate of reaction changes. So in that case, rate constant will also change. Okay. So for this point, we can also say that the value of the rate constant for a particular reaction, or we can say that for a same reaction, it changes with temperature. Now the next point, we can say that the value of the rate constant for a reaction, it does not depend upon the concentrations of the reactants. Okay, this rate constant, this K value, it does not depend upon the concentrations of the reactant. Next thing is that the units of the rate constant, it depends upon the order of the reaction. Now we will discuss this order of reaction now. Okay, till now you don't have any idea about the order of reaction, but now we will discuss about this order of reaction. So these are the characteristic properties of the rate constant K. Now see, the rate law and the law of mass action, they are not the same. Here you can see that from a particular reaction only, we have got two types of rates. This one is from the theoretical values, and this one is from the experimental values. So this rate of reaction, it is according to the law of mass action, and this rate of reaction, it is according to the rate law. So we can say that this one is according to the law of mass action, and this one is according to rate law. Right. So this is the theoretical value. These A and B, the molar concentrations of the reacting species, they are the theoretical values, and here alpha and beta, that is the molar concentrations of the reacting species, they are the experimental values. So in this way we can differentiate the rate law and law of mass action. Now from the rate law only we can express the order of reaction. So what is the order of reaction? It is the sum of the exponents, whatever exponents are there, the sum of the exponents to which the concentration terms in a rate law equation, they are raised to the power. So to express the observed rate of reaction for that particular reaction, we can say the sum of the exponents, it is the order of reaction. So for this particular reaction, the order is alpha plus beta. Let me give you some other examples, then you will understand clearly. Look at this equation. Here you can see that after theoretical balancing, here the number of bromide ions is 5, number of bromate ions is 1, number of H plus ion is 6, and here different amounts of bromine and water are formed. But experimentally it is observed that the rate law for this equation is different. So experimental rate of reaction for this case, it is rate constant. Now for bromide ion, the number of we can say the molar concentrations that have taken part in the reaction is only 1. Now for bromate ion also, here only 1 is the molar concentration, and for H plus ion it is 2. So the rate of reaction, the order of reaction with respect to bromide ion is 1, order of reaction with respect to bromate ion is 1, and order of reaction with respect to hydrogen ion is 2. So we can say that the overall order of reaction, it is the sum of the exponents. So here for bromide it is 1, for bromate 1, for hydrogen ion it is 2. So overall rate of reaction is 4 for this equation. Clear? So in this way we determine the order of reaction for each and every type of reaction depending on the experimental values of the different reactants which have taken part in the chemical reaction. Clear? But sometimes what happens, the expected order doesn't follow and there is some deviations and there is the difference between the theoretical value and the experimental value. Okay, I will show you the examples. Depending on the sum of the powers of the reacting species, that is the experimentally observed values of the reacting species, we can determine the order of reaction and we can express them as zero order reaction, first order reaction or second order reaction, like that. Okay, so here are some examples. Here you can see that when hydrogen and chlorine, they get mixed up in presence of sunlight, it is formed 2 moles of HCl. So here you can see 1 mole of hydrogen and 1 mole of chlorine will react to form 2 moles of HCl. So we can assume, or it is expected that theoretically if we say what is the rate of reaction, here we will say that 1 mole of this one, 1 mole of this one, that means the reaction order is 2. But experimentally it is found that it is zero order reaction because here the rate is simply the rate constant. Okay, so here no moles of the means experimentally we can say that alpha and beta, here whatever alpha or beta we take, here it is the sum is 0. So it will be the zero order reaction for this particular reaction. Again for first order reaction it is expected to be again the second order reaction because number of moles here is 2, but it is found that experimental value is 1. That means the rate of reaction here depends only on 1 mole of the concentration of N2O5. So we can say that this is the first order reaction. Now in case of this one, here it is expected that 2 moles of NO2 and 1 mole of F2, that means it is a third order reaction. But experimentally it is found that the rate of this reaction is 2, that is second order reaction. Okay. Some other examples are also there which are different from the expected order. So I will give you the examples. Look at this reaction, that is the decomposition of ammonia on a hot metal surface. Here you can see that either platinum or molybdenum or tungsten can be used as the catalyst and tremendous amount of heat and pressure are supplied for this reaction. Now it is from the theoretical values we can expect that the rate of the order of reaction can be second order. But what happens? Experimentally it is found that at very high pressure, what happens? On these metal surfaces the ammonia gas gets absorbed. Now at high pressure the surface of the metal is completely covered by the ammonia molecules, and on further increasing the pressure, that is the concentration of the that particular gas, it will not have any effect on the amount of gas at the surface. So we can say that the rate of reaction, it does not depend on the concentration of the reactant at all. Clear? So here we can say that the rate is given by this type. Here the rate of reaction, or the we can say, yes, the rate of reaction only, it does not depend on the concentration of the ammonia gas. So here again we can write in this way. Thus it is a zero order reaction. Clear? If we take the different example for, let's take the first order example. See, for the decomposition of nitrous oxide at very high temperature, here also from the theoretical value it is expected to be a second order reaction. But what happens experimentally? It depends only on 1 molar concentration of the reactant. So we can write that rate is equal to rate constant into N2O, concentration of N2O only. Okay, so this shows that the rate of reaction is this one and the order of reaction is simply first order, because here only one is present over there. So this is a first order reaction. Clear? Now the order of reaction can be a fraction also. So here we have till now we have seen that the order of reaction, they have the values of 0, 1, 2 in this way. So now we are going to know that how the fractional order of reaction is found. For this equation, the rate is given by, so the order of the reaction will be given by the sum of the powers. Here the order is equal to 1 plus half, that is 1.5. Again for some other reaction, so for this reaction also you can see that experimentally determined values are like this. So the order is the sum of the powers, and here it turns again a fractional value. So these are the examples of the reactions of fractional order. Clear? So in this way we can say that the order of reaction can be 0, 1, 2 in this way, or it can be also be a fractional value. Clear? Now we will learn the different units of the rate constant for the reactions of different orders. See, no need to memorize the various units for the different orders. You can simply calculate it, or you can simply get the proper units by deriving it from the proper rate equation. So let's take the example. For the means generally we can say that for a reaction of nth order, the rate of the reaction is given by dx dt, right? Change in concentration by change in time. So it is given by rate constant into concentration of the reacting species to the power the order. N is the order. So for nth order reaction, the rate is given in this way. Now we need to know the unit of the rate constant. So from here we can write that the rate constant is equal to dx dt into 1 by concentration to the power n, right? So here we can say that this dx means the change in concentration. So this one is also a concentration term. So this is concentration, and dt is the change in time. So again this is another time unit. Clear? And here again one concentration term is there. So from this one we can say that the rate of the reaction, that means the concentration, see here concentration will become 1 minus n, right? And time will be time inverse. Clear? Now concentration is given in moles per liter and time is given in seconds. So for zero order reaction we can say that this n is 0. Okay, so if we want to calculate the unit for the zero order reaction, then in that case the concentration will be moles per liter and here the power will be 1 minus 0, that means 1 only, and second inverse. Okay, so for zero order n is equal to 0, that means here it will turn mole liter inverse is the original concentration, means unit of concentration, and here it is 1 minus 0 and it is second inverse, that means it will turn mole liter inverse second inverse. Clear? Similarly for the first order reaction, here n is equal to 1, so the concentration term is mole liter inverse. For first order n is equal to 1 means 1 minus 1, it will turn 0, and here again second inverse, so it will be only second inverse as this term will turn 0. Clear? I mean the power will be 0, that means the whole term will be 1. So here only second inverse will be there for the first order reaction. Now for second order reaction, again this N is 2. Look at this, putting the value of N as 2, here it will turn -1, right? And again second inverse is there. So ultimately the unit for the second order reaction will be mole inverse. Here it is liter and second inverse. Clear? Now for third order reaction, similarly we can get the unit. Look at this, putting the value of N as 3, here mole liter inverse will turn -2. The power will turn -2. So we can write the ultimate unit for the third order reaction as mole -2 liter square and second inverse. Clear? Now in case of the gaseous reactions, instead of the molar concentration, we generally use the pressure in atmospheres. So the units of the rate constant will be different. Here we have written that the unit for rate constant is concentration to the power 1 minus n and time inverse. Now in case of the gaseous reactions, this concentration term will be expressed in terms of the atmosphere. So it will turn to be atmosphere to the power 1 minus n and time inverse. So similar to that of the concentration terms, if we express the units of the order of reaction according to the pressure conditions in case of the gaseous reactions, so for this we will get means for the zero order reaction, here moles per liter is there, that means atmosphere will be there simply, so it will turn to be atmosphere second inverse for the gaseous reaction. Now for the first order reaction, here is no molar concentration, that means for gaseous reaction again there will be no atmospheric condition, so it is similar in case of the gaseous reaction also. Now in case of second order reaction, again this mole inverse liter will be as that of the atmosphere, so it will be, in case of the gaseous reaction, it will be atmosphere inverse and second inverse, and in case of third order reaction it will be atmosphere to the power -2 and second inverse. So these red marked units are for the gaseous reactions, that is in terms of atmosphere, and these blue colored units, they are in case of the normal molar concentration terms in case of the general reactions. Okay, so these are about the units of the reaction rate constant for the reactions of the different orders. Clear? Now we will learn about the molecularity of the reaction. See, this concept will make your concept clear about the order of reaction, how this order of reaction and molecularity are different. You will learn about it in detail here. Okay, so first we need to know what is the molecularity of a reaction, and before that we need to know about the chemical reaction in detail. Okay, see, we have already discussed that the rate of reaction may not depend upon the stoichiometric coefficients of the reactants. Means in the balanced chemical equation, whatever the stoichiometries are, the rate of reaction may not depend on those values theoretically, right? This means that the balanced chemical equation, it does not show that how the reaction takes place. That means how much quantity of the reactants are ultimately used up for the complete chemical reaction, right? So from this we can say that it is very rare that the reaction may be completed in one step. Now the reactions which take place in a single step only, they are called the elementary reactions, and those reactions which do not get completed in a single step, that means which take more than one step, they are called the complex reactions. And in case of the complex reactions, whatever steps are followed, they are called the mechanism of the reactions, right? Now in class 9th standard, you have learned that what are the different criterias of a chemical reaction to occur, and one of the most common or one of the most important criteria for a reaction to take place is close contact, right? So we know that whatever the atoms or ions or molecules of a reactant, whenever they come in close contact, they collide with each other, right? and this concept gives rise to a theory called collision theory, which we will discuss later. But for now, keep it in mind that the number of atoms or ions or molecules which collide with each other simultaneously to form a successful chemical reaction, it is called the molecularity of a reaction. Am I clear? Whatever the atoms or ions or molecules are, those molecules or atoms or ions which take part in the chemical reaction to form a successful chemical reactions, they are called the molecularity of the reactions. Clear? Now, in case of a simple reaction, that is the elementary reaction, all the atoms or ions or molecules of the reactant present in the balanced chemical reaction, they can come together simultaneously to collide with each other. So such reactions take place in a single step only, and the molecularity for the elementary reactions, that is the simple reactions only, it is simply the sum of the molecules of different reactant species which are there in the chemical reaction. Okay, let me give you some example for the decomposition of O2F2. See, this is the complete reaction only and the balanced reaction also. So here, as the concentration of the reactant is only 1, so it is called the unimolecular reaction, as the molecularity of the reaction is 1. Okay, so here we can write that molecularity is 1, that is unimolecular, and this reaction take place in a single step only. Again, we can take the example of dissociation of HI. So for the dissociation of HI dissociates to form hydrogen and iodine, right? So in this case also, here we can see that 2 molecules of HI gets dissociated to form hydrogen and iodine separately. So in this case, the molecularity is 2, and it is called the bimolecular reaction. Okay, here 2 moles of HI has been dissociated. Clear? Again, we can take the example of the reaction between NO and O2 to form NO2. On balancing, it will turn like this. So here, for the reaction between NO and O2, the molecularity is 3. You can see here 2 moles of NO and 1 mole of oxygen has been reacted here completely. Okay, so molecularity is 3. That means for this the term is termolecular. Okay, so in this way we can determine the molecularity of a reaction. For the elementary reactions, the order of the reaction and the molecularity of a reaction is same, because here only the number of molecules of the reactant species are taken, and as the reaction is elementary, both the molecularity and order is same, because each reactant has the same stoichiometric coefficient as represented in their balanced chemical equation. Means both theoretically and experimentally the values are the same. Now there are some reactions in which all the atoms or ions or molecules as represented in the balanced chemical reaction may not come together to collide simultaneously. Okay, for example, look at this equation. Here you can see that in the reactant side 5 bromide ions are there, 1 bromate ion is there, and 6 hydrogen ions are there. That means here overall there are 12 ions, right? So it is impossible for all these 12 ions of the reactants to come together simultaneously to collide. So such reactions are called the complex reactions, because these reactions, they take place in several steps, and such reactions are different from the elementary reactions. In case of the elementary reactions, the overall reaction take place in single step only, and for this type of reactions, as all the reactants, they don't react together, means all the ions are not reacting all together simultaneously, so they react in several steps. at several rates. So each of the steps will have separate rate of reaction, and molecularity can be defined only for an elementary reaction and not for the complex reaction. But yes, for the complex reactions, each and every single step can be means for each and every step we can determine the molecularity of those steps, because those single steps can be regarded as the elementary reaction for that particular step. Clear? So the different elementary reactions of a complex reaction, they do not take place at the same rate, and the overall rate of the reaction depends upon the slowest step. So we can say that the slowest step is called the rate determining step. This is very important. This rate determining step gives us the ultimate rate of the reaction. Okay. This will be more clear to you if I give an example. See, here is the example of the thermal decomposition of N2O5, that is dinitrogen pentoxide, and this is the balanced equation for this thermal decomposition. Now here you can see that 2 moles of N2O5, it gets decomposed to form 4 moles of NO2 and 1 mole of O2. So we can write the rate of reaction according to the rate law as K N2O5 only. Why is this so? This is because here it is the experimentally found value. Okay, so this reaction can be written in 2 steps. So the different steps of the reaction mechanism are, for the step 1, here first N2O5, it forms NO2 and NO3. Okay, this is the slow step. This reaction takes place in a slow rate. And for the second step, here this N2O5 reacts with NO3 here, and then it forms 3NO2 and O2. So this is the fast step. So as I said that slowest step is the rate determining step. So for this particular reaction, this is the rate determining step. Hence we can say that this reaction is unimolecular reaction or the reaction of first order, because this reaction, this step shows the rate determining step. As I said that rate determining step gives you the proper rate of the reaction. So here we have taken it as the first order reaction because depending on the rate determining step, that is the slowest step, we will determine the ultimate order of the reaction or ultimate rate of the reaction. Clear? So in this case or in this way we can determine the several order or molecularity of the reactions. One important thing that you need to study is the difference between order and molecularity of a reaction. See, this type of question is there for your ISC for 2 marks, and I will provide you the points to be mentioned if the question is there for your exams. So after this video is over, please go through the Google Classroom where I have posted the difference between the order and molecularity of the reaction. Okay, and in the next class we will start with the integrated rate equations. So that's all for today.